Welcome to this video on forces on a rigid body. It is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. In contrast to the video on forces at a point, we now have three equilibrium equations at our disposal when we consider equilibrium of a rigid body. The equilibrium equations for forces in the horizontal and vertical directions remain. The new equilibrium equation relates to moments. Equilibrium of moments is called angular equilibrium. It means that the moments that try to rotate a rigid body clockwise must be matched by the moments that try to rotate the body counterclockwise. In this context, a moment can be an applied moment at a point, or it can be a force acting at a distance to the point where we consider the equilibrium of moments. The fact that we must consider moment equilibrium at a selected point contrasts with the two equilibrium equations above. Consider this example, where a 3 kN force is acting on a rigid body that is 6 meters long. In all the examples in this video, we assume that we know which forces may act, even if we do not know their value and sign. In this case, we assume that the body is supported in such a way that there is a vertical reaction force at point A and another vertical reaction force at point B. There are nuances in how we address a problem like this. It is here selected to start by establishing moment equilibrium about point A. That means we multiply the applied force by the distance to that support, and we subtract the contribution from the reaction force at point B times the 6 meters arm to that force. The reason why we subtract is that the reaction force at point B gives a moment about point A that is in the opposite direction of the moment coming from the applied force. It does not matter if we adopt the opposite sign convention here. If we let the moment from the applied force be negative and the moment from the reaction at point B be positive, then we get exactly the same answer. The calculations show that the reaction force at point B is 2 kN. Next, we employ equilibrium in the vertical direction in order to find the reaction force at point A. The inclusion of the applied force and both reaction forces leads to the conclusion that the reaction force at point A is smaller than that at point B. The next example is a similar demonstration of the selection of a point about which to take moment equilibrium. Absolutely any point would do, the result would be the same. Here, moment equilibrium is again taken about point A that leads to the result that the reaction force at point B is 12 kN. Equilibrium of force in the vertical direction now gives a minus sign in the result. Examining that equilibrium equation shows that we have arbitrarily chosen the downwards direction to be positive. As a result, the negative sign tells us that the reaction force at point A is actually downwards, meaning that this support is in tension. The objective in the next example is to determine the bending moment that is acting inside this rigid body at the midpoint between point A and point C. As a matter of standard procedure, we start by finding all the forces that are acting on this rigid body. Moment equilibrium about point A suggests that the reaction force at point C is 6 kN. Notice that we here find the resultant of the uniformly distributed load and multiplies that resultant by the 3-meter distance from point A to that resultant. Equilibrium in the vertical direction reveals that the reaction force at point C is the same as point A. That makes sense, because this problem is symmetric. Next, we cut the rigid body where we want to find the moment that must be acting inside the rigid body at that cut. We then set up angular equilibrium about point B in order to find that moment. Notice again how we employ the resultant of the distributed load when we calculate the moment of that load about point B. The result is that there is a 9 kN moment at the cut marked with a dashed red line. The positive value indicates that it is indeed acting to give tension at the bottom and compression at the top. As an aside note, you would get the same value of this moment if you simply say QL squared over 8. When the distributed load, Q, is 2 kN per meter and L is the 6-meter length, you directly get the 9 kN result. The QL squared over 8 formula is derived exactly as in this example, and it is an important value because it is the biggest moment value that can appear in any beam with uniformly distributed load, except cantilevered beams. The next example is intended to show that it does not matter where a point moment is acting, but we still must select a point about which to take angular equilibrium. Which point we select does not matter, but we must select a point. Here we take moment equilibrium about point A. Notice that the 10 kN meter point moment enters without any arm or reference to its location. It simply tries to rotate this rigid body clockwise by a 10 kN meter moment. Moment equilibrium about point A, or any other point on this rigid body, gives a 5 kN force at point B and an identical force at point A with opposite sign, which here means tension. The next example appears in any exposition of beam theory, such as the Euler-Bernoulli beam theory. However, here, we simply want to do equilibrium of a rigid body. The way this problem is set up, we assume the vertical forces are in opposite directions with the same value. That means the body is in vertical equilibrium, as well as in horizontal equilibrium because there are no forces acting in that direction. Moment equilibrium about point A includes the 10 kN meter moment on the left and the 15 kN meter moment on the right, naturally with opposite signs because one is clockwise and the other is counterclockwise. Carefully note how the vertical forces, which represent shear forces if we use the language of beam theory, here gives a clockwise moment equal to V times 1 meter about point A. The result is that the shear force, V, is 5 kN. The number 5 is interesting, because that is the difference between the moment value on the left-hand side and the right-hand side. Looking into topics covered in other videos, the shear force is actually the change in moment divided by the length of the beam segment, unless other loads are acting. In this case, the change in moment is 5 kN meter, which divided by the 1 meter length is 5 kN. Finally, here is an example for those who like to climb ladders. Suppose you weigh about 100 kilograms, which is about 1 kN, and you have made it halfway up the ladder. We must assume there is no friction between the ladder and the wall, so we cannot count on the ladder being carried by any vertical force at point B. That means the ladder is carried by 3 forces. A horizontal force at point B, a vertical force at point A, and a horizontal force at point A. Notice from these 3 equilibrium equations, which include all the equations that this video started with, that there is the equivalent of a 12.5 kilogram force needed in the horizontal direction at the base of the ladder. Notice in the next slide that the horizontal force at the base increases as you climb up the ladder. When a person weighing 100 kilograms is at the top of the ladder, then the horizontal force at the base is the equivalent of 25 kilograms, which is twice what it was when the person was halfway up. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.